Man is finding new ways of probing the cosmic unknown. Around Earth, tenuous matter forms great spheres in space. 60 miles up, the ionosphere begins, stretching 200 miles or more, a region of electrically charged particles formed by radiation from outer space. A region important in world communications, because radio waves which do not follow the curve of the Earth can be reflected from the ionosphere. But sometimes great solar storms disturb the region. Radio signals fade and disappear. To forecast such turbulence, sounding stations around the world send constant signals into various layers of the ionosphere and record the echo. But these ionosondes cannot probe beyond the layer of greatest electron density, and more information is needed from above. In 1958, a program of topside sounding is conceived by the Defense Research Board of Canada and the National Aeronautics and Space Administration of the United States, NASA. Canada has a special interest in the project because radio blackout is most frequent in the North Polar regions, and so DRB undertakes to build a satellite for the sounding. Work begins in 1959. Design and construction of the spacecraft, to be called Alouette, the Lark, are put in the hands of a group of young engineers, men like John Marr and Colin Franklin of DRB. The USA will launch it. The plan is to launch the satellite from California into polar orbit. The vehicle is a two-stage rocket, Thor Agena B. The Thor burns until final velocity is reached. Then explosive charges release the Agena and spacecraft, and Agena's engine ignites. In the thin upper air, friction is slight. The protecting shroud is ejected. At cutoff, Agena is coasting. 48 minutes later, it reaches orbital altitude over Madagascar. After a final boost in orbit, a spring separates the satellite. As it spins, long antennas are driven out. 1 hour after liftoff, the new satellite is sweeping around a polar orbit 630 miles above the Earth. It will circle the globe every 105 minutes for centuries, transmitting signals to telemetry stations for at least 1 year of research. As the sounder moves into range, a command is sent out, and the long antennas transmit a pulsed radio frequency signal to the ionosphere below. At the same time, the pulses are put on a very high frequency signal that will pierce the ionosphere. The sounding signal is reflected, and the echo received by the satellite is transmitted to the ground. The time lag, about 1/100th of a second, giving the height of the ionosphere. Thus, transmitting a continuous signal, pulse and echo 60 times a second, the satellite reports on the top profile of the ionosphere, hour by hour, to telemetry stations around the globe. At the same time, it measures 3 other phenomena: radio noise due to rays from cosmic space, whistlers or radio signals caused by lightning which move along the Earth's magnetic field, and trapped particles, one of the causes of ionization in the ionosphere. Since there is no precedent for the topside sounder, rocket testing of the antenna system developed by the Canadians is an important preliminary. From Wallops Island, Virginia, rockets carrying the newly designed equipment are launched into the upper atmosphere. Signals that come back prove the system is definitely feasible. At DRB's telecommunications establishment near Ottawa, a structural model, a prototype, and 2 identical flight models are built. 2 half-shell spinnings form the skin of the aluminum spacecraft. The entire load is supported by a core. The central structure holds the antennas when stored and the batteries. Platforms on each side carry the transistorized sounder and the 3 other experiments. Standby units are provided to be switched on in case of a failure in space. It's a close fit. Power for the instruments is provided by 6,500 solar cells on the shell, which convert sunlight into electricity to charge the batteries. Inside temperature is maintained by polished aluminum end caps. Of unique new design are the long sounding antennas of thin spring steel, which form a tube with an overlapping open seam. During launch, they will be wound on drums as flat strips, like a carpenter's tape rule. Canadian industry contributed to the project by developing and building a number of important components. The prototype is given a centrifugal test simulating the vertical thrust to be experienced by the spacecraft during launch. Performance of the telemetry equipment monitored during test is completely satisfactory. A spin test simulates conditions as the satellite, spinning at 120 RPM, will be ejected into orbit. As the sounding antennas unwind, the spacecraft slows to its final speed, 1.5 RPM. Because of Earth's gravity, the antennas can be extended only 9 feet without support, but the test shows smooth operation so far. Next comes a full extension test. An electric motor drives the antennas out. Because of gravity, they must be supported. To conserve power, antennas should be half the wavelength transmitted. In this case, a length never before attempted in a spacecraft. The design works perfectly. The span is 150 feet from tip to tip. At another DRB research center near Quebec, performance is tested in a vacuum chamber, simulating conditions in space. Unknown factors may arise. Materials may sublimate at low pressure. Hundreds of wires from the instruments permit the designers to check performance during test. Air is pumped out of the chamber and an artificial sun shines through a port. To provide illumination evenly to all the cells, the satellite spins slowly as in space. The spheroid shape serves two purposes: easy access to electronic equipment, and secondly, illumination of a constant percentage of the surface as the spheroid tilts. Current generated by the solar cells is checked, and housekeeping data such as temperature in various parts of the spacecraft is observed. At Goddard Space Flight Center near Washington, NASA provides test facilities not available in Canada. Here, shining satellites in various stages of development are joined by Alouette. Like a giant automobile wheel, the satellite must be balanced. At full speed, the amount of imbalance is measured and correcting weights are added later. Although the spacecraft weighs 320 pounds, less than 2 pounds is needed for balance because of careful calculation during design. The highly sensitive solar cells, the elements most likely to be damaged by vibration, are checked with simulated sunlight after every mechanical test. Finally, the Alouette is mounted on a shake table, which sets up vibration like that experienced during launch. The sounding antennas are checked before the test, which is one of the most severe the spacecraft will undergo. Measurements of the vibration applied and resultant vibration in the satellite show that no serious resonance will develop. Housekeeping data checks show solar cells, batteries, and other components all performing normally. Alouette passes with flying colors. Protecting plates are again placed over the delicate solar cells for the final move as the months of tedious testing draw to a close. After 2 years of design, construction, and testing, Alouette flies across the continent to Vandenberg Air Force Base in California. A conventional turboprop aircraft of the RCAF carries the bird of space that soon will soar imponderous. Alone, the little sphere will penetrate the intangible mathematics of the cosmos. Yet, in the crowded environment of Earth, its sensitivity must be protected. There remain 6 weeks of final testing. The Thor Agena B rocket waits in its 150-foot gantry to carry one of the most complex satellites yet put into orbit. Alouette is seated on the spring that will separate it from the rocket. The shroud that will protect it from frictional heat in the atmosphere during launch is closed. The press enjoy the free tradition of science. DRB's Dr. John Chapman draws attention to the flags of the cooperating nations. Alouette's investigation of the upper atmosphere makes Canada a leader among the nations in space research for purposes of peace. Hours before liftoff, the scientists responsible assembled in the Mission Direction Center for the countdown. Keith Brown of DRB is mission director. Day spins into night over the Pacific coast. NASA's Dr. Dryden and Dr. Zimmerman of DRB watch and wait.
Fuel counter to 0. Fuel counter to 0. Pad propulsion engineer. Pad propulsion engineer. Verify TV ready. TVs are ready. INF? INF here. Place all 3 position switches off. All 3 position switches are off.
19. Go ahead. Check 19A, B,
On time mark, it will be T-minus.
Converter 4 alone was on battery 4.
9, 8,
And NRC operation is normal for this phase of the launch.
3,
Check 19D and E.
1. Mark.
The beacon is minus 65. Spacecraft temperatures are within tolerance.
60 seconds from now, we'll be picking up the terminal top. Spacecraft or launch conductor, are you ready? Spacecraft ready. 6, 5, 4, 3, 2, 1. Lift off.
South across Antarctica and north across Africa, toward the North Polar region. From beyond the imperceptible surface of Earth's atmosphere, signals come to Resolute, one of the 13 telemetry stations around the globe which record Alouette's observations. Signals in the language of the stars, observed, recorded, and translated into a language understood by scientists who speak the many tongues of men.